Our goal is to find power series representation for ln of 1 plus x. Okay. Remind yourself of geometric series. For a geometric series, we had the summation of x to power n start from 0 to infinity, which is 1 plus x squared, the rest of the terms, and as long as the absolute value of x is less than 1, this guy is convergent to 1 divided by 1 minus x. Here I have ln of 1 plus x. Can I use geometric series and find a power series representation of 1 over 1 plus x? Let us try. First, we try to find power series representation for 1 divided by 1 plus x. 1 over 1 plus x can be written as 1 divided by 1 minus x. So basically, we are following this pattern. The pattern is as follows. The summation of the quantity to power n and start from 0 to infinity as long as the absolute value of that quantity is less than 1 is equal to 1 divided by 1 minus that quantity. So this is the pattern that we're following. From geometric series, we find a pattern and we're happy with that pattern. We're going to use it. So take a look at this function, 1 divided by 1 plus x, that can be written as 1 over 1 minus negative x. So the quantity that you're looking for, this box, is minus x. So following the same pattern, this guy is equal to the summation of the pattern, which is minus x, to power n, and n starts from 0, goes to infinity. You can rewrite this as well. So 1 divided by 1 plus x can be written as the summation of negative 1 to power n, x to power n start from 0 to infinity. So I found power series representation for 1 divided by 1 plus x. So far, we found power series representation for 1 divided by 1 plus x. And I expect you to ask why we are using 1 divided by 1 plus x. This is ln of 1 plus x. Now remind yourself of, recall that. If you have the integral of dx divided by 1 plus x, it is equal to ln of 1 plus x plus c, as long as x plus 1 is positive. So what does it tell me? It tells me, hey, if I take the integral of both sides, it must be equals to ln of 1 plus x. Very good. So if we take the integral of both sides, we have ln of 1 plus x. Smart move. Take a look. I'm going to erase this and rewrite this guy here for you. So since 1 divided by 1 plus x can be written as the summation of -1 to power n x to the n, and start from 0 goes to infinity. I can write this guy, first of all, as -1 to power 0, x to power 0, plus -1 to power 1, x to power 1, plus -1 to power 2, x squared, plus the rest of the terms. So 1 over 1 plus x can be written as 1 minus x plus x squared minus x cubed plus x to the 4th minus x to the 5th plus the rest of the terms. Now take the integral of both sides. What do you have? You have the integral of 1 divided by 1 plus x, which is equal to the integral of 1 minus x plus x squared dx. So you have 1 divided by 1 plus x, which is, and then we take the integral with respect to dx. So with respect to x, so you have dx, and you have 1 minus x plus x squared minus x cubed plus x to the 4th, and so on. So I'm not going to copy down everything, plus dot, 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 dx. And on the right hand side, you have basically the integral of your power series, the summation of -1 to power n times x to the n dx. So from calculus, we know that this guy is ln of 1 plus x, assuming 1 plus x is positive. The integral of 1 is x. The integral of x is x squared divided by 2. The integral of x squared is x cubed divided by 3. The integral of x to the 4th is x to the 3rd is x to the 4th divided by 4 plus the rest of the terms. So what do we see here? We have the summation of -1 to power n x to the n. We are taking the integral of this quantity. So it means that if I just move the integral inside the sum, I have the summation of the integral of -1 to power n, but we are taking the integral with respect to x, everybody. It doesn't change -1 to power n at all. So what do we have here? We have ln of 1 plus x equals to, you can copy down the rest of the things here, or just copy the summation and start from 0 to infinity of -1 to power n x to n plus 1 divided by n plus 1, and that's it. You can add the constant of integration at end, and then note that the absolute value of x must be less than 1. Why is that? If we go back up here, remember that the absolute value of the quantity must be less than 1. But the quantity here is -x. The absolute value of -x must be less than 1. So absolute value of x is less than 1, or x is bounded between -1 and 1. So the interval of convergence is -1 to 1. Open interval, -1 to 1. So let us recap what we did here. We wanted to find the power series representation for ln of 1 plus x, and we went back, used geometric series in general. Remind yourself of the definition of geometric series. This is the summation of x to the n from 0 to infinity. As long as absolute value of x is less than 1, it converges to 1 divided by 1 minus x. We have a pattern here. The pattern says the summation of any quantity to power n, as long as the absolute value of that quantity is less than 1, converges to 1 divided by 1 minus that quantity. Well, I started by using 1 divided by 1 plus x. 1 over 1 plus x can be represented by the summation of negative 1 to power n, x to the n, and start from 0 to infinity. And the quantity, the absolute value of the quantity must be less than 1, or your absolute value of x is less than 1, or x is bounded between negative 1 and 1. Why we used 1 over 1 plus x? Because we remind ourselves of the integral of dx divided by 1 plus x. It is nothing but ln of 1 plus x as long as 1 plus x is positive. So, take a look at your question again. ln of 1 plus x can be generated using the integral of this power series. So, if we take the integral of both sides, we have ln of 1 plus x. Since 1 over 1 plus x can be written as the summation of negative 1 to power n x to the n, and start from 0 to infinity, we take the integral of all sides. The integral of 1 divided by 1 plus x with respect to x is the integral of this polynomial, this sum, which on the right-hand side is the integral of this power series. The integral of dx divided by 1 plus x is ln of 1 plus x, assuming that 1 plus x is positive, and the integral of 1 is x. The integral of negative x is negative x squared divided by 2. The integral of x squared is x cubed divided by 3. The integral of negative x to the third is negative x to the fourth divided by 4, and so on. And the integral of the sum can be calculated just taking the integral of the general term here. So ln of 1 plus x on the left-hand side is equal to the summation of negative 1 to power n, and the integral of x to the n is equal to x to n plus 1 over n plus 1. As long as the absolute value of x is less than 1, ln of 1 plus x is represented by this power series.